So in this video, we're going to start talking about some of the important features of graphs aside from the x and y intercepts. We've talked about the x and y intercepts already. Now we need to talk about the other parts that really make the shape of the graph. So let's say I have a function, and I'm just going to make one up here. Let's call it, negative 3x to the fourth plus x plus 2. Okay, so there's my polynomial. And I want to know what this thing looks like. I can probably figure out some x-intercepts if I factor it. Now, it's not going to factor nicely because I just made it up, and who knows where the x-intercepts are. Let's pretend, just pretend we had some x-intercepts here, like that, maybe a y-intercept. Looks like the y-intercept is 2 because of that 2 right there. But those aren't really the important part for this discussion. Right now I want to talk about the shape of this thing. So, forget about the intercepts for a moment, what I'm saying. How do we figure out the shape of this function? And I mean generally, if you take a big step back and we imagine zooming out from the picture. So all the little x and y intercept stuff is really a small part of the overall graph that we're drawing. Well, what you do is you imagine what happens to this graph when x gets very, very large, like infinity. Well, then you have negative 3 times some big number. It doesn't have to be infinity, but it's a big number, plus these other things. And a big number to the fourth power is much, much bigger than just a regular big number. Okay? Which means, for the most part, in an approximation, we can forget about these other things. And really, as x gets very, very big, this function is going to appear simply to behave as negative 3x to the fourth. Okay, it's not exact, but it's going to appear to behave that way. This is why the power function is so important. If you remember, this is the power function right here, this negative 3x to the fourth. And that's where you should always look when you're wondering what kind of shape this curve has. Now, there are 4 categories of shapes. This is rather nice that they work out so easily. And I'm just going to draw the 4 categories of shapes right here. Every single graph is going to fit one of these shapes. So you have things that look like x squared. Okay? You have things that look like negative x squared. And that's just flipped over upside down because of the negative sign. Then you have things that look like x cubed. And that's, remember this sort of wiggly snake picture. And then the upside down version of that. And if you think about it for a second, you'll realize why everything has to be one of these 4 shapes, approximately. Because your choices are up and up, down and down, down and up, or up and down. There's no other combination other than these 4 combinations that you can have. Now, the power function of a polynomial determines what its end behavior looks like. This guy right here is called positive even. That's the name of this shape. Now, it's called even because of the exponent. It's a 2. But the shape would look the same if it were x to the fourth or x to the sixth, or 17 x to the squared. Okay? It doesn't matter if there's a number in front of the x that's an odd number. It's totally irrelevant. The important part is it a positive number, and is the exponent even? Likewise, over here, this is called negative even, because the coefficient is negative, but the exponent is an even number. And then over here we have positive odd, because the exponent is odd, and even if you had x to the fifth, it wouldn't look a whole lot different. It would just look maybe like this. Okay, but it would still have the general shape. And then over here you have negative even. Okay, so those are the 4 types of end behavior. And we've gone over the power functions, we've gone over the names. Sometimes people talk about end behavior in terms of its limit notation. In other words, how you would describe it using limits. And I'll give you one example. You could probably extrapolate the rest from this one. Let's say we're looking at a positive odd function. Okay, remember this is positive odd. The way I would describe positive odd behavior using limit notation is I would say the limit of x, f of x, as x goes to infinity. Well, as x goes to infinity, you can see the function is going up towards infinity itself. So you would write it this way. And in the limit of x going to negative infinity, you can see down here, when x goes to negative infinity, y also goes to negative infinity. And of course, this description right here will change for each one of the end behaviors, but you can probably, as an exercise, figure that out.